Good afternoon, everyone, and welcome to another of our TDS webinars for 2024. It's always great to have you here with us during your lunch break or wherever you're sitting outside New Zealand. So today we have a presentation about the 90 Devonport Road project, which is a hybrid steel timber building, and Nicki Vance from Tauranga is here to talk to you about that. But before we go into that, some announcement from our end. So we already have locked in the next webinar speaker, which will be about good and bad connection design. As we know, the devil is in the detail when it comes to timber design, and we have Pierre Kinville from University of Auckland, who is sharing his experience with what works and what doesn't work when it comes to connection design. This is more like generic examples. It doesn't necessarily look at brittle failure modes, which is Pierre's expertise. Future webinars are about the quality assurance and manufacturing of CLT. And we also want to have a special session about carbon and sustainability in timber. And we have a few others in the pipeline, but they haven't been confirmed as yet. Other events of interest, especially when you are Christchurch or Canterbury based, on the 7th of May, Woodwork South is organizing a seminar. So it's at 3 p.m. here in Christchurch. And we also have the pleasure to host Shilling Pei from the University of Colorado. And he's visiting here at the University of Canterbury. I'm obviously Christchurch based, so that's why I'm saying here. And he will have a CSOC TDS seminar on the 9th of May, where he's talking about the Neri Tallwood project. So you can see this, I think, 10-story shake table test, which they're performing currently at the University of San Diego in California. As usual, if there's any topic of interest you would like to learn more or you want to share with the New Zealand and wider audience, please get in touch with via the TDS homepage. We are obviously more than happy to accommodate any of those requests. Thanks obviously to the TDS committee to continue doing these webinars, and also to you attendees for joining. That's always good. And also a big thank you to our TDS sponsors. Without them, we wouldn't be here. We have Future Build, LVL, Mytech, Simpson Strong Tie, Ixlam, iBuild, and Rotoblast. Right, so back to today's webinar. Again, it's about the 90 Devonport Road hybrid steel timber office building. And we have Nicki here from Tauranga. So Nicki has 10 years of design experience between New Zealand and the UK. And she has interest in heritage building, but is also working in the computer modeling space and obviously carries out construction monitoring. More recently, she's interested in large-scale timber structures and obviously using timber in order to have a lower carbon design to promote sustainability. The webinar today, or the talk today, is about this 8-story building, which is in the heart of Tauranga, and probably have seen or heard about it via LinkedIn or other events. Nicki has already spoken to the Auckland audience at the 2nd of November last year during the hybrid seminar. And today is a bit of a repetition of this presentation, but obviously a few months have passed since, and the building is now under construction. And Nicki can also share a little bit more about the challenges encountered during the construction of the building. The building itself, obviously, Nicki will explain a bit better about the details. It has LVL beam and columns, CLT floors and cores, and it has steel K braces. So based with all that, I hand over to Nicki, and yeah, enjoy the webinar today. Thank you, Nicki.
Thanks, Daniel, and thank you for everybody who has joined us online and given up your lunch breaks, or if you're sitting at your desk eating a sandwich, hello to you too. So as Daniel said, I'm talking about 90 Devonport Road today, which is a new office building currently under construction in Tauranga. So just a little bit of a structure of the talk. I'm going to start with talking about the project, why hybrid, some of the challenges that we've encountered, what worked well, a few comments about looking forward, and then hopefully at the end we'll have some time for some questions. So start by saying a little bit about the team. So the building is developed by Willis Bond, based out of Auckland, the developer. Warren Amani, also based out of Auckland, is the architect. Becca, primarily based out of Auckland, and Tauranga. They're doing services, fire design, passive fire, and Green Star. LT McGuinness is a contractor in their new Tauranga arm, RLB QS, ourselves as Structural Engineers, obviously, and the building is going to be leased to Tauranga City Council as their offices. So where are we? Unsurprisingly, we're on Devonport Road, which is in kind of the heart of Tauranga CBD, and the site also overlooks quite a steep cliff, which goes down to the Strand and the water. Devonport Road, or 19 Devonport Road, is the first in a series of new developments in Tauranga seeking to kind of regenerate the heart of the city. That is what the site looked like when possession was taken. So it had been used as a kind of meanwhile space for quite a number of years. You can see in the background that big Pahutakawa tree and the kind of that which sits on the cliff edge down to the water. This is the grand architectural vision, or what we're aiming for, and then that's our Revit model. So not quite as polished, but you can see the general form. So we're an 8-story timber building, as Daniel said, primarily LVL beams and columns. We've got a few glulam columns to the external area, and some of those are double height. Starting as any good engineer would in the ground, we sit on a large number, 139 concrete piles, which range in depth from 15 to 23 metres, 750 diameter CFA piles. The ground was not great under the site, probably slightly worse than we initially anticipated, and there was potential for liquefaction at quite large earthquakes. And so in the end, we decided to design for that and deepen the piles to get through some of that liquefaction. So here is a nice architectural shot of the reinforcing. They're not highly reinforced piles, they're just very long, and you can see the pile cages there in the foreground. The piles are generally connected by single, double, and 4 pile caps connected together with a series of ground beams. We were really conscious when we undertook the design of this project that we're based in Wellington. Obviously, the site is in Tauranga, so we wouldn't be able to be there all of the time to, pop down to site with half an hour's notice. So that really drove us towards keeping all of the foundation and concrete details as regular as possible and limiting the kind of number of specials, because we knew that, we weren't there to answer questions, and we'd have someone else looking at it on our behalf sometimes. I've included the shot in the bottom just because the concrete work was really, really fantastic. The quality is great, and it seems a shame that it's all covered up. So just to give it a moment in the sun. So here's our typical floor plate. We are sitting at about just less than 30 metres in one direction and 48 in the other. It's quite an open floor plate with a central core. And we range in bay dimensions from 7.2 typically up and down the page, and there's a range across the page, the shortest being 5.6 and the longest being 8.6 metres. And that's the same type of shot, but from our structural drawings. The building has a raised floor on top of the CLT, which gave us the opportunity to hide some timber drag members, which are primarily there to help the diaphragm. As Daniel mentioned, we've got a CLT core, and this is the same drawing but without the floor. So we've got primary beams running up and down the page and secondary beams across, and then we've got some of the shortest bays, which is basically CLT only, and the CLT spans much more than the typical. Typically we're doing 2.4 metres, and then these longer ones are 5.6. And the primary reason for doing that was to aid the services strategy. So this was something that we considered right from the get-go, is this idea, because it's so hard to put penetrations in timber, we really thought about services reticulation very, very early. And the idea is that services rise in the rises and then are distributed along the services corridors, i.e. the bays with no secondary beams, and then they can poke out through the primary beams, which are set down and distributed that way. It also means that we can have, thinking about the services strategy early meant that we could expose more of the CLT, the soffit of it. So the placement of services was really important. And here's that kind of diagrammatically in terms of the services zones and the set down primary beams. That's what it kind of looks like in a typical connection. So we've got a notched secondary beam with reinforcing screws screwed into our primary set down beams, and then coming into the column, again, we've notched the column to house the beams. And that's kind of the same type of thing, just exploded, and what it looks like in real life. As Daniel mentioned, we've got K-frames that are distributed in pretty regular arrangement throughout the building, which obviously helps the CLT diaphragm, because obviously they can't span quite as far as a concrete diaphragm, so well-distributed lateral load resisting elements are key here. And that's what the K-frames look like in elevation. And again, as a 3D shot. And here's a picture of them being craned into place. We knew that we were most likely to have a local steel supplier, in our case Jensen's. So what that meant was we could design the K-frames with a minimal amount of splices. The dream was to try and get them to cantilever through the splices for a temporary works perspective and just prop for straightness, but we couldn't quite make the numbers stack up on that, unfortunately. The facade system is a typical curtain wall. It steps out as you move up the building, so we have extended our CLT out to pick up the facade progressively as you move up the building. I'm going to give my voice a break and show the little time lapse of progress on the building so far. So we started in about January last year. And yeah, here we go. So you can see once we're out of the ground, it moves incredibly quickly. Once we're doing the timber superstructure, the main constraint really was actually just supply of materials. And once Red Stag, who were the CLT manufacturer, once they got their second CNC machine, yeah, we were really progressing fast. LT McGuinness had a warehouse in Tauranga, which they used to store the timber, which is key on a site like this. Right, so I've explained about the building. Now we're into why hybrid. So the first part of that is why timber, and why were we lucky enough to be able to design this really interesting building. The original scheme for the site was actually a steel building, but the client, Willis Bond, was able to kind of develop a slightly more premium product with the use of timber and the aim for 6-star Green Star, which as of last month we have achieved. And obviously a part of that is all of the timber in the building. We had a bit of a play early doors on the iStructD carbon assessment tool, just for the structural parts and the kind of A modules. I would really recommend anyone, if you want to have a bit of a play, it's a great tool. It's much more simplistic than something like LCA Quick. And of course, with carbon assessment, it's not about the real round numbers, it's more about, you know, the difference between them. So what you can see in this graph is our steel alternative along the top, and then these two other lines are the different CLT suppliers. So either Red Stag, who we ended up going with just down the road in Rotorua, or Xlam out of Australia with their dirty power obviously penalises you quite a bit. So this next slide, I think that when a new material kind of comes on stream, there's always the first few iterations where we try and replicate what we're used to doing using the new material. I don't think as an industry, as architects and engineers, we've really got to the bottom of what a timber building form looks like for a, you know, regular everyday building. There is still a slight tendency to replicate what we've always done in terms of bay dimensions and building form of a concrete or steel building. The same type of principle is demonstrated here in Iron Bridge in Shropshire. So this was, as the name suggests, the first iron bridge in the UK, and you can see that you know, it still has that common form of kind of a brick or stone arch bridge. So then why hybrid? Why not just all timber alone? The first one is to do with simplicity. I sit next to Rowan, my colleague, who is doing Living Power, which is an absolutely amazing building, and that's all timber, but that is extremely bespoke, extremely complicated, and we were trying to do something that's a little bit, I think it's been described, less ball gown and more t-shirt, so something, you know, more regular, more everyday, and something that can be replicated on, you know, a larger scale if we get the system right. So there's the simplicity aspect. There's also an aspect of, we knew that we were going high, so 8 stories in mass timber. And so that was kind of the hard bit of this project. You know, we don't have to do all of the hard things all at once, all in one project. So trying to keep things simple really pays dividends, particularly due to the sheer volume of the building and the amount of connections. So the more we could keep them the same, the easier. We did use steel in a few other places where it made sense. For example, that's a shot of a steel strap which connects the discontinuous timber diaphragm ties. The last one I've termed is the purity trap. And so we had a situation where we had timber columns on the plant room as well. You know, we're doing a timber building, so let's make it all timber. And the contractor came back and said, well, look, from a program perspective and a weather tightness perspective, we'd like to switch these ones to steel, which we did. In my opinion, you know, if we're doing, it's far better to do 100 buildings that are 80% timber than 50 buildings that are all timber only. So yeah, we think this is quite a good system of having the K-frames and then the timber gravity structure. So moving on to some challenges. The first one, as we're probably all very familiar with, is fire. You know, it was very much a state of flux, I think, in New Zealand at the moment, and this was prevalent through our kind of late design and consenting phase. The requirements, particularly with regards to hidden connections, seem slightly out of step with some of the international examples that we're seeing, whether that's because we're ahead of them and they've got to catch up, or whether we've got different regulatory requirements. I'm not 100% au fait, but you know, you can see there the typical example of castellated beams sitting below CLT, and you know, the American example of all their 5/1 housing. Anyway, what it meant for us is we have this kind of unknown of what happens in a fire when our timber beams are sitting in our steel shoes, which are connected to the K-frames in some locations. The aspiration was to intumescent paint the K-frames and have them on display, but we couldn't find any research during design which talked about how timber functions when it's in contact with steel and under load. So there's a lot of thermal models that talk about the heat transfer between steel and timber, but not when the timber is also loaded, and whether or not that leads to, as I've kind of tried to draw there, accelerated charring or not. Unfortunately, at the end, we couldn't quite get there over the line with having the K-frames on display in inch meson. So we've boxed them out for the most reliable performance, but maybe the next one. Another challenge was the facade. So facade engineers, or certainly in our case, got involved very late in the design process and were not particularly experienced in working with timber. We had the facade system is, your typical curtain wall. It just has slightly different bracketing details for connecting to the CLT rather than a concrete slab. And so they had pretty tight deflection tolerances for us, which we were able to meet even with the creep factor. But what kind of surprised us a little bit more through the design process was the lack of continuity at the columns. So because we're stopping our beams each side of the column, which also happens often in a steel building or a concrete building, but you get continuity, much more continuity through the concrete slab than we do in our case with the CLT. So what that meant was we had to do an exercise of looking at the facade panels and looking at the deflected shape of our kind of edge beam and CLT and the deflection profile, and then looking at what rotation and that means that the panels, did they open or close depending on that deflection profile, which was an interesting exercise. In the future, if I was to do this again, I'd try and get in contact and get the facade supplier to appoint their engineer really early so that they can feed into those discussions right in the early stages of design. Another challenge is consenting. So I think we're all aware with 3603, that lovely simple standard that we still have, but it's a little bit out of date, particularly in relation to mass timber. It's older than a lot of people in our office. So we've got that on one hand. We've got 1720.4, the fire standard, which is still not cited, and then we've got the rest of 1720, and then our European screw supply. So we use Rotherblast screws on this, and so obviously the ETA as well for screw design. So that's all, it's not nearly as clear as if you were just doing a steel building or a concrete building where things are much more prescribed. There's certainly still a level of judgment. And we had a peer review for our building, both from a geotech point of view, a structural point of view, and a fire point of view. So that was a lot of extra review on this one. I've put in this slide just to plug this book. I've just read it a couple of months ago, and it gave heaps of interesting background on a whole bunch of different things that are of interest to us that deal with timber, right from why New Zealand has so much radiata pine, where did that come from, to historic arm wrestles over timber treatment or untreated timber. But the relevance to this was it has a great section on the move to performance-based building codes and what that meant when that was introduced, probably before a lot of our times now in the early 90s, and how it kind of left the territorial authorities with a whole new system that they didn't necessarily get in much training on, and the kind of dearth of education that's come through the industries with the closure of the Ministry of Works and those different pipelines. So yeah, recommend this book. It's not nearly as dry, no pun intended, than what the title suggests. I've put it as a challenge. is peer review is, we're moving towards, as we do more things that aren't well covered in the standards, of needing more and more peer review, or when territorial authorities aren't confident in their checking procedures. We're being asked to do more peer reviews, which on general terms I think is a really good thing. It's always really good to have another engineer, someone that's outside of your own organization, having another pair of eyes, but it's a really difficult thing to estimate the time and the cost. And when you're a peer reviewer and you are asked to review someone else's design and effectively sign the PS2, you are taking a kind of sense of responsibility for the design, and in a sense, and what is stopping us kind of ratcheting towards conservatism, because not being involved directly with the design team and understanding other pressures, that might be architectural, cost, construction. At the moment, as there's not really any mechanism for the peer reviewer to not just say, well, yeah, let's just put a bit more fat into it. So I think as a wider industry, that's something that we will start to have to grapple with more. Interesting to hear that MB are thinking about putting together some guidance on potentially partial peer reviews, which might help in situations like this as well, where we've got really known seismic system, and then it's more about the interface with some more bespoke bits and pieces. And moving to on-site challenges for moisture management. Obviously, we're not building in tents here in New Zealand, and I think there's still a kind of sector-wide, particularly people who have come from housing, this idea, well, timber just gets wet all the time and then it dries out, which doesn't work very well for mass timber. So this was a challenge, but I'll also cover in the what worked, because I think the guys on site did a really fantastic job. The last thing I've got for a challenge, something that we didn't really give a lot of thought to at the time, was a bit surprising. Probably shouldn't have been, but the timber panels that we had to the core, they're so light that they basically act as a massive sail, because they don't have a lot of self-weight, unlike a concrete panel. So what that meant was it had to be a super, super still, calm day for these to be installed. So which we managed to get a few of those in Tauranga. I don't know how you'd fare here in Wellington. So moving on from challenges, what worked really well? The first one was the team. The design team, the construction team has worked really well. We all get along, and we actually like each other still, despite the fact that we're just reached the roof stage of the project. And I think that's so important, working with people that you like. Now, nobody wants to work with assholes, so we've been super lucky. We were doing the design at kind of the tail end of COVID, and we were based from an engineering perspective here in Wellington, and everyone else was pretty much in Auckland. So we did a lot of it over Teams and Zoom, which definitely has advantages, but I think there's nothing like getting around the table with some actual physical drawings, scribbling on them, tossing ideas around. And so if I was to do it again, I would try and do a few more in-person workshops, particularly when you're doing something new. It's really important to have a good team dynamic and empathy for other designers, because there's no project that always goes 100% right. But I think when you're doing something new, there's probably more times where you're likely to say, oh, look, that didn't work out quite how I was expecting. I need to change this beam size, or I need to shift this thing, or that type of thing. So when you've got good relationships, it's so much easier to pick up the phone and ask for that without feeling like it's a massive imposition and people are going to get angry with you. The other part of that is providing explanations. I think when we're familiar with something, we sometimes don't remember what it's like not to know, or for things not to be self-evident. So explaining to people, for example, why penetrations are so hard in timber helps them understand why you're being so, tough about a certain aspect, why it's different to a typical steel building. So explanations, I think, are really, really key as well. We had local eyes and ears on this project, Richard from Asterix, who was fantastic. I can't stress how beneficial it is to having another engineer on site that you trust to do inspections. All of his site reports and things lived under ours. We're still the ones issuing the PS4, but to have somebody that can pop down to site, and particularly when you're in the ground and doing all the concrete work, is really good. And Asterix also did the temporary works design, because it's really important to have your temporary works engineer, in my opinion, based close to site, so they can pop down with 20 minutes notice rather than us flying up from Wellington. I have to thank my colleague Chris for the great concept that we started with. It really made the whole process so much easier, and part of that is actually allowing enough time for concept design. As we move towards more of these new timber buildings, it's going to take more time up front, because there's lack of rules of thumb. We don't have that kind of intuitive knowledge so much than what we do for our traditional concrete or steel buildings. And it requires a kind of systematic thinking early in the design process, that kind of collaborative, integrated design. And of course, as you only need to do it once, but you're probably all aware that a lot of these timber members are connection governed. It's about how much timber you have to how many screws you can fit in. So that's a kind of difference to a traditional concept design, where you could just size your steel beam and work out the connections later. So it's having to do a couple of those typical connections really much earlier means that it's important that you allow yourself enough time in concept stage. Another thing that worked really well was, in my opinion, our drawings. I think our drawing set is a really, really good on this job. Anthony, our drafty, worked extremely hard, and they look really fantastic. And part of that is that because it's quite a simple building, and we tried to keep a minimum amount of difference. We're trying to keep things as typical as possible. What that means is you have less drawings, and the drawings that you do have, you can make better. So yeah, that worked really well. I put moisture management in as a challenge, but it also was something that worked really well. I was so impressed with the guys at LT McGuinness, in that they, timber's quite new for them as well, but what I was impressed with was their ability to think of a solution, implement it, and then most importantly, interrogate if it was working, and if it wasn't, then change it, as opposed to just coming up with a moisture management plan, being like, this is what we're going to do, here, we've done it, oh well, that's it, wash your hands of it. So the kind of stepping through and trying different things worked really well. So we've got a few examples there. I think the pool noodles to the K-frame, our column top hats, which should really be on the columns rather than in the photo, but just prevent water in the kind of running into the straws and the end grain of the columns. We had an Aotearoa membrane go down on level 4 over the Christmas period, where we didn't have a lot of people on site to do the sweeping of the water off the floors. What we found is that due to the size of the floor plate, it was actually better to have some scupper drains in the floor, so that we could have some places to push the water to and just drain it all the way through the building. And then you can see in that last picture, we've got some temporary steel flashings, which were sitting on the edge of the building before the facade went up, because we were having problems with moisture coming through in the gap between the facade and the edge of the floor before the next level of facade was on. Looking forward, so yeah, obviously we'd like to see more of these hybrid buildings. I think it's worked really well. What that means, though, is that we're there's a potential that we become a bit constrained in our timber supply, with only one CLT supplier and 2 LVL suppliers. What does that mean if suddenly we do want to do 100 buildings that are 80% timber? The other thing too is as we move forward and we get more experience, I think ECI will become more valuable. So for us, we're still in the early phases. A lot of construction companies haven't done a lot of timber, so they're not bringing as much in the ECI space as what they would do in probably some other projects. I think they will really come to the fore for screw selection, because at the moment, we're basically, as engineers, deciding the screws, and there are a lot of them, early in the design office, really based on who has the easiest manuals, and the good tables, and so because it becomes so hard to change later in the design process. So if we have more ECI and knowledge at the beginning, that will probably influence things. Similarly for the moisture management, that's only going to improve with time as we work out what works and what doesn't. And lastly, just, I think there's ongoing conversations about sustainability on one hand versus, the new national seismic hazard model and the potential if we do go down the route of implementing the new TS. So I think that's where I see things heading, if what we need a little bit more discussion on. I'm lastly just going to finish with some other photos. So we've got a shot of the CLT core panels, and an interior shot where you can see one of the timber cords sitting above the CLT. I didn't mention it before, but from a moisture point of view, not the greatest idea, because we kind of ended up creating little pools between the cords. So in the future, there might be something to do with the sequence of putting them down, but in our case, we needed them to tie the floors together, or certainly some of them from a temporary roots perspective. And then here's a lovely architectural shot of the facade that's going in. The fit out is starting for Tauranga City Council, so that's a couple of shots. And then lastly, a shot from the strand at the bottom of the cliff with the big putakawa tree in the foreground that we saw earlier. So with that, I will ask if there's any questions. Thanks.
Nicki, thank you so much for your insight and the very honest feedback you're giving and the experience learning you learned throughout this journey. I think it's very valuable for all of us to hear how others went through the design of this building. So there's quite some questions coming in. Let me see where we start. So you started off talking about, material and white timber. Obviously, you did mention other materials were considered. I think there was a steel concept. Maybe you can give a little bit more feedback on what other materials have been considered in the concept stage.
Sure. We actually, somebody else actually did a steel scheme for the site first. And then it was decided that the client decided that they would like to pursue something different, and the 6-star Green Star for a somewhat different offering. So that kind of led us down the timber path pretty early. Yeah.
And another question still about timber as such. You showed the iStruct-E calculator. And the question is, have you used any other tool like the New Zealand Green Building Council tool, or there's the Naylor Love tool, which are all simplistic? And for the Green Star rating, you have been approved. What tool have they used?
So I did also use the Naylor Love tool as a bit of a cross compare with the iStruct-E one. And got reasonably similar results in terms of the quantums. The Green Star tool, I actually don't know what tool that they used. I'd have to look it up. there's only, for the Green Star, it's a surprisingly small percentage of points that you get through actual carbon accounting. A lot of it is to do with, it's everything from bike parking and waste management. So it's very holistic. The structure plays a not insignificant, but a small part in the wider scheme.
Perfect, thank you. So there's a few questions about the seismic or earthquake design, trying to summarize them up for you. But first of all, roughly what are the seismic parameters? I think that mainly refers to ductility. And second, what's the load transfer between the diaphragm and the actual K-braces?
Sure. We're slightly over a ductility of 3. We're IL2. The load is transferred from the diaphragm into the K-braces. I'll just see if I have a shot in 2 ways, depending on where the K-frame is sitting in relation to the floor. So we've got SHS stubs, which are bearing on the diaphragm. We have 2 cases. The one here, they go out sideways, and then when the K-frame beam is sitting below the CLT floor, we then have upstand stubs, which again are in a pocket in the CLT.
Thank you. That's quite an interesting, innovative detailing. But yeah, you need to be innovative with timber, and especially when you just start doing hybrids. So no, good solution, I think.
Thanks.
Another quick question was, what software did you use to model the building?
Well, we didn't really use a lot of software beyond Space Gas. We can do a simple ETABS model, but we used ETABS to analyze the CLT diaphragms, which was the most complex modeling part of the whole job.
Thank you. Another question was about acoustic performance. Was there any specific consideration on the acoustic performance, floor-to-wall connections, for instance?
Not particularly. It's in a because it's all one tenancy. There was, you don't have to deal with intertenancy issues. And also, if we just move back to the floor plan, the tenant introduced a secondary open stair and a void, which was a little bit of a curveball very late in the design stage, particularly from a fire point of view. What that means is you get a lot of noise transfer through levels because you have a void. So acoustics, I think it's much harder when you're thinking about this type of system for, say, an apartment, where acoustics between different apartments becomes much more of an issue and much more sensitive.
Yeah. Now, related to that, so perhaps acoustic wasn't as governing in this building. What about vibration, footfall vibration?
Yes, so we do have a raised floor, which helps from a damping point of view on the CLT. We were a little bit concerned with the long span CLT, that 5.6 meters. So we did some testing, is maybe too strong a word, but we organized to get some panels up at Red Stag, kind of point supported, and walked around in them and tried to measure the frequency and see what that was, and they seemed to perform quite well. What we were able to do is because we'd done Scion before, we had an model, or we had an in real life example of a building. So we took the clients and some of the users there and said, this is what a timber building feels like. It's quite different to a traditional building. This is basically what you can expect. So we can back calculate that those vibration parameters. And so we then said, well, okay, if that's our limit of vibration performance and we want to make sure that our building doesn't do any worse than that. But I have to say, walking around on it, it feels pretty solid, even without the partitions and the raised floor on yet. I mean, so I'm pretty comfortable with where we're sitting. But as with everything, vibration is a little bit of a expectation management and psychological, rather than the engineering still pretty much a black box, I think.
Yeah, no, unfortunately, I agree with your comment, but I think it's also important to, as you say, manage the expectation, at least talk them through. And if you have a sample building like you had, even better. There's another quite interesting question, which you might want to explain a little more. So the question is, you obviously, because of the services, you have the secondary beams sitting on top on the main beams, and I assume they're notched slightly, or maybe not.
Yeah.
But obviously, compared to a steel building, you're much deeper depth. So question one, what is actually the height between the bottom of the main and the top of the secondary? And is that something which the Green Star rating looks into? I don't assume so, but yeah, any consideration
Yeah,
about
sorry. I should have said, yeah, we have a didn't say that we have a 4 meter floor to floor height and or 4.5 on the ground to first. So there is that bit of extra depth, compared to a typical office building, which helps put in, that we can have the depth of the structure. So because we've got a 600 deep, as you can see there, 600 deep secondary beam, which is notched 350 into the 800 deep primary. So you can do the maths in terms of how much of that 4 meter floor to floor that eats. But because a lot of this timber is on display, we're only having a ceiling every second bay, which is sitting round about that secondary beam level. It means that the space still feels quite open, and you get the nice feeling of the timber beams. The thing with I will just say, because I forgot to say it during the talk, is that because we've got quite deep secondary beams at 600, they're treated from a sprinkler point of view as a downstand wall. So you can see slightly in this photo of the small sprinkler holes, which were pretty much the only penetrations through the timber beams that we had, with the exception of two penetrations down on level 1 for drainage pipes, which had to be to a full. So yeah, you are kind of eating more into that, your floor to floor with structure. But when it looks so beautiful, it doesn't matter, does it?
Well, except the question also refers to the height is costly in a CBD because you want to optimize the space. But I think it's a bit of a trade-off, and services are a big consideration. So I think they shouldn't be ignored when you do timber buildings. One question was about the building looks somehow regular. Was there any consideration of making it a modular construction?
I mean, it's all very component based. So there's things that are quite, all of the beams are all individual elements. The short answer is no, we didn't really consider it modular in the sense of a whole lot of different squares, but we didn't really need to. I think it's so fast as a component based thing, and probably our experience with the panels probably suggests that smaller, less volumetric things are probably better because they're so light.
Yeah. That's my own question now. Roughly, how long did it take to install one floor, including the columns and beams? Just roughly.
In the order of kind of 2 weeks, if that.
Yeah, it's pretty good. So I keep going because we have a bit of time, if that's okay with you, Nicki.
Yeah.
With more questions, yeah. What allowance was made for timber drying and shrinkage in use?
So what we were primarily concerned about was that the timber, particularly the LVL members, would get wet and undergo volumetric change, and then effectively never regain their previous smaller smaller volume, which hasn't really eventuated. The CLT did have higher moisture content, but we're trying to get that down, that moisture content down, before the raised floor goes on, and so we're not expecting a huge amount of additional drying during use.
Okay, thank you. Another question was, you showed the core panels, the CLT core panels, which were acting as a sail. But aside from that, were they participating in the lateral load resisting system? Or was all the load taken by the K-frames alone?
All the load can be taken in the K-frames. So we have panelized the core so that it doesn't attract a heap of load. And so it's only, we worked out the screw capacity between panels and the relative stiffness. Yeah.
So essentially the column shaft, the core went for the ride together with the building.
Yep.
Yeah. You did mention modeling and briefly diaphragm before, but there's a specific question about what analysis method did you use for the timber diaphragm design?
So we kind of, there isn't really a full, you can't pick up a textbook and just look up what to do. So we kind of had an approach that we've kind of come up with. It's a variation on kind of the typical strut and tie, but for the timber CLT panels.
Mm-hmm. For the audience, there is a little bit of guidance in the FP Innovation Modeling Guide, which could be used, but as Nicki was saying, there isn't a one-fits-all type approach, unfortunately, especially also because diaphragms can be made of different timber materials and perform differently. There's two questions which I'm going to summarize, Nicki, about costs. Was there any comparison done in terms of how much the timber costed compared to traditional? And was there any cost analysis done? Was there any, is there any information you can share with that?
Probably not so much. It's probably getting outside of my wheelhouse as a structural engineer, I must say. I think it is still the case that timber buildings are generally slightly more expensive than a steel building, though the price of steel has increased so much, maybe that isn't as valid anymore. But what you do have is such a program saving, because if you can put a floor up in 2 weeks, so there may be a more upfront cost for the timber procurement, but you may actually save with a building that is delivered quicker. So it's really quite difficult to make those judgments, I think, certainly for us as engineers.
Yeah, that's true. We are often not really part of that discussion in terms of costing, unfortunately, or fortunately in part as well. There's a fire question, which I cannot ask you a fire question. So aside from the boxing of the EBFs, was there any other detailing implication as a result of the new fire guidance? For example, treatment of exposed timber elements, surfaces, and so on and so forth.
So we had a 60-minute fire rating to the building, and all of our screws are recessed 50 millimeters, which works out as your 60-minute, and plugged. So we basically don't have any exposed steel connections, and all of the ones where we're pocketing the K-frame stubs into the CLT, they're all covered up with plasterboard as well. So there's that bit of it. 60 minutes is getting pretty tough in terms of the sizes of timber members and the sizes of columns that are produced, particularly the width. There are some small areas that are intumescently clear-coated the CLT soffits in public areas. That's more of spread of flame issue. And then we did have to, when they were doing the burnout calcs, we did have to end up putting some fire protection to only one level to the soffit of the CLT which is a combination of jib board and Ryan, their fire bats, which are a bit lighter.
Mhm. Thank you. That's good learning on that as well. There's more questions coming in as we speak, but I'm trying to conclude that session soon. Let me see what else. There were two questions about foundations. So first of all, a bit more generic. What's your feel in terms of, does a timber structure reduce the demand on your foundations? Do you think there's a cost benefit there? And then more specific to your building here. So you have mentioned and shown the concrete piles. Was there any other improvement system, like ground improvement system, like stone columning or stabilized cement columns? Was there consideration around that?
So to answer the first question, I think very much there is an advantage to a timber building from a sheer weight perspective, and therefore a reduction in foundation costs. And also from a seismic demand point of view, if you've got less weight, then there's less, overturning forces and tension and compression that are imparted to the foundations in that sense. So to answer the first question, the short answer is yes. The second part of the question, ground improvement was looked into. It wasn't quite the right site here, but we are using it in other sites in Tauranga at the moment.
Mm-hmm.
The wrap system, the gravel columns.
Yeah. Right. Last few questions. What was the design drift for the building under ULS? Like, what percentage of drift did you design the building to? If you remember.
Yeah, it's been a while. From memory, it's not a particularly low drift building. I think we're sitting in the order of 2% or something like that. So
yeah, I guess with 3.5, with activity of 3 point something, that's probably not unexpected.
Yeah.
Let's see what's left. Now that you've completed design, is there any component shortfalls you think warrant some more product development or R&D moving forward, so that you as a designer have better tools and better products to specify?
I mean, the holy grail is some type of intumescent paint that can keep temperature down to less than 120 degrees, but that's probably slightly physically insurmountable potentially. We don't have a lot of. There isn't a bunch of kind of widgets or anything, because it's quite simple, the connections in terms of the amount of screws and the taking everything and bearing. So nothing really springs to mind. I think there's probably some development that could happen around facade to CLT interfaces and that kind of bracketry, but that's probably all that springs to mind at the moment.
Yeah. I want to add to that, if I can, the 120 degrees on the steel plates for fire, I find it very conservative, but it's based on very little research, and therefore the standards committee obviously put something in which is on the conservative side. I think a lot more work needs to be done. So a bit of a message to the fire engineers or fire researchers out there: we need better testing, or more than testing, we need design principles, how we can make our steel to timber connections work a bit better moving forward. That's definitely something where our industry needs to work into a bit more. So I think I conclude the session with this. Apologies to the questions we have not answered. I've tried to prioritize the more fundamental and important ones. Nicki, thank you so much again for making the time and sharing your experience, your knowledge on the Tauranga building. I'm looking forward to see it then finished and open and running, and perhaps we manage to do a site visit, if that's possible, up in Tauranga for the local engineers moving forward. Yeah, so thanks again, and thanks everyone for joining, and I'll see you on the 16th of May for the next webinar. Thanks and goodbye.